Hi guys, today we're talking about Rutherford's model of the atom and the experiments that he did to get him to his model. Remember, we've already talked about two models. We've got Dalton's model, which is the solid sphere, where he thought that there were no other particles inside of that atom. That's all there was. It was just a solid mass. You couldn't get any smaller. And then we had Thomson's model, where he discovered that the atom actually has a negatively charged electron in it. And he also knew it was neutral overall. So he knew that there were negative electrons embedded in this positive substance. That's the model that Rutherford started with because he worked under Thomson when he started out. This picture shows the setup of his experiment. He had at the center of this a sheet of gold foil. Remember, gold is an element. So it's just one type of atom all packed together. There's no space between those atoms. And remember, he has Thomson's model of the atom in mind. So he's thinking that these atoms are evenly distributed, positive and negative substances. There's no concentration of mass. All the particles are spread out. This alpha source here shoots this super fast, high velocity, really tiny particle at that gold foil. This particle, the alpha particle, is the nucleus of a helium atom, so it doesn't have any electrons on it. It's just got 2 protons and 2 neutrons. So 4 little teeny tiny particles going really fast at this gold foil. And then around the outside of it, he has this zinc shield screen. It's fluorescent. So because it's fluorescent, when these alpha particles hit it, they make a little flash of light. So you can see if the particles are going to hit behind the gold foil, if they're going to go straight through it, if they're going to bounce off. He'll be able to see it because he looks for a flash of light on the screen. It has to be dark for him to see this. So picture him sitting in a dark room for hours with this alpha particle source holding this zinc screen, looking for teeny tiny flashes of light on it. Very long process. So what do you think would happen to the particles in the atoms if there was no empty space? I changed the question. I said, what would happen to the alpha particles if the particles in the atom are evenly distributed, right? So he's starting with Thomson's model, and he thinks that those positive and negative particles are evenly distributed. He thought that all of those alpha particles would just go straight through because there's no concentration of mass to stop them. Those positive and negatives are spread out. And he's shooting a little particle that has 2 protons and 2 neutrons, and he thought that those particles would just go straight through because all the particles in an atom, he thought, were evenly distributed. What actually happened is most of the particles did go straight through. He expected all of them to go straight through, but he did not expect any of the alpha particles to bounce off and come back, and he didn't expect any to get deflected to the side. So this totally shocked him. He he imagined this as shooting a bullet at a piece of tissue paper and having some particles come back at you. He didn't think it was possible. He thought that this bullet would just go straight through the tissue paper. But if we take a closer look at the atom and what we know about it now, you have a concentration of mass inside the nucleus. So Rutherford really discovered the nucleus here. He saw these alpha particles come in and get deflected, that would be this one, get curved off and go off at an angle. And he saw other ones hit the nucleus head on and bounce straight back. That didn't happen too often. But when he saw that, he was discovering this nucleus. You've got this concentration of mass here. And remember that these alpha particles have a positive charge because they're just protons. They're 2 protons and 2 neutrons. And protons have a positive charge. So that when this positive charge comes in, if it gets deflected, that means that you've got two particles that have the same charge. If this nucleus, well, we know the alpha particle is positive, so that means that this nucleus must be positive too if it's deflecting a positive charge. We also know it must have a really high mass, a really concentrated mass for this little teeny alpha or this alpha particle to hit it and then bounce off without moving the nucleus. Now remember, most of the alpha particles actually do go straight through. And that means that most of the atom is actually empty space if they're not hitting anything and just going straight through. When they do hit a nucleus, which wasn't very often because the nucleus is very small, they get deflected. Remember, that means that the nucleus is positive. And very rarely they would bounce straight back, meaning that that nucleus doesn't take up much space. Only very few of those alpha particles hit it straight on and bounce back. Okay, so here it is, written out for you to write down. Most of those alpha particles went straight through the gold foil. So that means that the atom is mostly empty space. We're breaking this up into evidence and reasoning to kind of help you with those claim evidence reasonings we will write. So his evidence, what he saw, is that those alpha particles went straight through. He could see that with the flash of light, lots of flashes of light straight across from that gold foil. And his reasoning is that that must mean the atom is mostly empty space because the alpha particles aren't hitting anything. There's nothing there for them to hit. He also saw that only a few of those particles were deflected off in different directions, like this one that came in and then went off at an angle. That means that the nucleus has a positive charge. And really, when you do your reasoning, you would do more than that. All right, it means that nucleus has a positive charge because the alpha particle has a positive charge and the alpha particle is deflected by the nucleus. So those particles must have the same charge. They're both positive. Only very few of those alpha particles go straight back. That means that the nucleus is very dense. You can't move it. It's a very high concentration of mass. That's how I worded it before, but that definition of a high concentration of mass is very dense. And it's very, very small. All right, so let's combine this with what we already know. Thomson's model has evenly distributed negatives and positives. Right? He didn't call this the proton yet because the proton hasn't been discovered, but positive goo and then negative electrons distributed in it. The updated model, Rutherford's model, is you've got an atom with mostly empty space. And then there's a small solid area in the nucleus where you have a concentration of a positive charge. James Chadwick in 1932 elaborated on the nucleus. He discovered neutrons. So eventually we figured out that they're protons and they're neutrons inside that nucleus. So now we've pushed those electrons out of the nucleus. They're no longer evenly distributed, but now they're pushed outside of this nucleus, and we've brought all the protons and the neutrons as a concentrated mass inside of the nucleus. So now, subatomic particle overview. Remember, sub means less than, that prefix. Atomic is atom. So these are particles that are less than an atom, particles that are smaller than an atom. We've got three of them. The proton has a positive +1 charge, and this is the mass in AMUs. These will round to 1. So protons essentially have a mass of 1 atomic mass unit, and we'll talk about what atomic mass units are later. if you were to figure out the mass in grams, it would be really, really, really small. So they came up with this atomic mass unit. So we're not working with extremely small numbers. The neutron doesn't have a charge, also in the nucleus with the proton, and essentially has a mass of also 1. So basically the same mass as a proton. And the electron has a negative charge, -1, and it has a very, 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 very small mass, which it does have mass, very little mass, but we'll round it to 0 and say it doesn't have mass, even though it does have a tiny bit. Okay, we'll stop there.